Okay, we're going to work 3.19. At this point, asks us to calculate each of the following. This problem is a lot like 317, except there are subtle nuances that make it a little bit different, and I want to point those out to you, okay? And part A asks us how many grams are present in 8.42 moles of chromium 2 sulfate decahydrate. We're going to figure this out, okay? Now, this problem is a really good example, starting to be a really good example of why you need to know previous subject matter from the course to successfully solve a problem you're facing, okay? I've been alluding to this kind of all along, that if you pick up things as we go, it's going to help you. And now I think this problem really demonstrates why that is. You may know mathematically how to go from grams to moles or moles to grams. Maybe you can even compute molecules or formula units, and you're really, really good at that. But if you get this problem on an exam, and you are unable to write the formula for chromium 2 sulfate decahydrate, if you can't write the chemical formula for that, you will be stuck. And you may get the problem wrong because you couldn't write the formula. So this is a really good example of how being able to write formulas, knowing that nomenclature, is also super crucial. You cannot rest thinking that you're safe if you can do the mathematical portion, because oftentimes problems are kind of integrated like this as a whole. You'll see that on homework, and you can see that on an exam. All right, so I wanted to point that out to you here at the start. If you cannot write the formula, you will be stuck, okay? Let's see why that is. Well, mathematically, we always start with what we're given, this 8.42 moles of the substance. And then, of course, we want to go to grams. A common way to do that is to multiply by the molar mass of the compound. But the problem is, and maybe you can set this up, the problem is you need to know what number goes right here. And you can only figure out how many grams per mole for this compound if you can write the formula. Right? So we have to have the ability to do that. So we think about it a little bit, and we say, okay, chromium, Cr, the problem specifies it's what? Chromium plus 2. I'm also dealing with sulfate, and this is the big one that I think students might struggle with. You have to remember that the sulfate ion is one of those polyatomic ions, SO4, with a 2- charge, okay? So if you can get to this point, you're probably pretty golden, because now you can say, hopefully you are, right? Because that's the hardest part. Because now you can say, oh, a +2 and a -2, they balance each other, and that's to formula my ionic compound. But you can't forget that it specifies we've got a hydrate, which means what? We've got to write dot some number H2O, and this is decahydrate. Boy, there's a lot of water associated with this. Dec is the prefix for 10. So this is the formula then for this material. So you got to add up the parts. So now we can start listing the parts that we need to add. We've got 1 mole of chromium and a mole of this stuff. And it looks like we've got 1 mole of sulfur and a mole of this stuff. I'm going to do the oxygen contribution from here first, and we'll add some more in later, okay? But from the sulfate, I've got 4 moles of oxygen. It looks like from the water now, boy, I've got 20 mole of hydrogen, right? 10 times 2. And I've also got an additional 10 moles of the oxygen. So these are all my parts that I have to add up, okay? This isn't 40, this is 4 oxygen, okay? So if I add up all those parts, the molar mass that I've gotten is 328.22 grams per mole. And if I multiply out to figure out what the mass of 8.42 moles is, I get 2763.61 grams. This is how many grams are contained in 8.42 moles. It's an easy problem mathematically, just to work on your calculator through multiplication. But again, the trick to this, if being able to write the chemical formula. If you cannot do that, you're not going to be successful, okay? Moving on. Part B. All right, so in part B of problem 319, we're told that we've got 1.83 times 10 to the 24th molecules of dichlorine heptoxide. And we want to convert that into grams. Okay. How do we do it? Well, start with the number that we know. Now, the first conversion hopefully is pretty straightforward. If you're ever given the number of molecules or the number of formula units, you can always convert to moles by remembering Avogadro's number, 6.023 times 10 to the 23rd. There are always that many particles in a mole. So if we divide by that number here, we find that we've got a little over 3 moles of this material. 3.038 to be exact, okay? Now, nothing has impeded us so far from figuring out how many moles of this material we've got based on the number of particles. So again, we start by writing, well, we know 3.038 moles for a molecule. And ultimately we want to go to grams, so we're going to have to do a moles to grams conversion. To do that, the mole units will cancel, but we need to know how many grams per mole. We need to know the molar mass of the compound of interest. So again, we've got to figure out what it is. We were told in the problem we have dichlorine heptoxide. We have to be able to assign the molecular formula based upon that name. This is a little bit easier, I think, because well, dichlorine is Cl2. We've got oxide and heptoxide, so that's Cl2O7. That's our molecule of interest. So again, to find the molar mass, we simply add up the parts. I've got 2 moles of chlorine atoms per mole of this compound, and the formula states I've got 7 moles of oxygen. So 2 parts chlorine, 7 parts oxygen. Add up those numbers from the periodic table, those molar masses. When you do so, you get 182.9 grams per mole. If you multiply that by 3.038 moles, you end up with 555.71 grams. Of the dichlorine heptoxide. That's how many grams is present in a 1.83 times 10 to the 24th molecule sample. Simple as that. But again, you really need to know how to write the chemical formula from name. Otherwise, you'll be stuck. Okay, let's look at part C. got 6.2 grams of a compound. Let's see, what am I told in the problem here? I'm told 6.2 grams of lithium sulfate. So we specify lithium sulfate. What am I asked to compute? Go to the number of moles and the number of formula units. So two things here. So I got 6.2 grams of the salt lithium sulfate ionic compound. It's a metal on a polyatomic ion, and I want to go to moles and number of formula units. So how in the world can I do this? Well, I've got a mass. It seems like we've done some grams to moles conversions before. To accomplish that, we divide by the molar mass. Problem again, I need to know what that molar mass is. Okay? Now how in the world can I find the molar mass for this stuff? Well, I need to write the formula. Okay, lithium is Li, sulfate is SO4. What are the charges involved? Sulfate's -2. Lithium, one of those group 1 metals, so it's +1. Okay? Now how do we make the charges balance to write the formula? Well, I can't change the charges on anything. They're innate to that material. Okay? So I got to keep the -2, and each one of these is +1. But I certainly could do Li2 SO4, and that would balance the charge. Of course, doing this is necessary because ultimately what I want to do is add the parts, add the components or the ingredients to lithium sulfate so I know my molar mass. So it looks like I've got 2 moles of lithium per mole of that compound. I'm going to have 1 mole of sulfur, and I'm also going to have 4 moles of oxygen. Those are my ingredients to make 1 mole of lithium sulfate. Okay, so if you add up all of the component parts, I get 109.94 grams per mole. This conversion factor then allows us to convert to mole units. According to my computation, I have 0.0564 moles. Of this compound. So that answers part of this problem. But we're also asked how many formula units. If I were to count formula units. Now remember, formula units are a lot like molecule analogs, but just for ionic compounds, right? How many repeating ionic clusters do we have, if you want to think of it that way, okay? So how can I figure this out? Well, I can figure it out because I know that I've got this many moles. And for every 1 mole, I have Avogadro's number, 6.023 times 10 to the 23rd formula units, because that's what defines the mole. So I simply need to multiply the number of moles I've got by Avogadro's number, and I'm in business. So it'll tell me how many repeat copies of this stuff I've got. Do the math, it's 3.40 times 10 to the 22nd. Formula units. And that's my answer for part C. Okay? Now, part D is actually going to expand upon this work. Let's see what we're specifically asked in part D, okay? The number of lithium ions. I'm asked the number of sulfate ions. I'm asked number of sulfur atoms and number of oxygen atoms. In that same sample from part C that we just talked about. Now, in that sample at the tail end, I hope that you remember we just decided we had 3.40 times 10 to the 22nd formula units, okay? That bit of information is crucial for us because we're dealing with that same sample and we're just going to basically convert to atoms of different materials here, okay? So how do we do that? Well, the first thing that I want you to key in on, again, is the formula for the compound. Now, there we were dealing with the lithium sulfate, remember? When we were writing the formula, we had to put the 2 here to make the charges balance. Same compound. To answer part D, we're really going to need to pay attention to the numbers in that formula, how and what ratio the elements combine. Because we want to know how many lithium ions are present in this many formula units of this, okay? Well, let's think about that for a second. So I know I've got this many formula units of this compound. Can I convert to simply a different unit into the number of lithium ions or charged particles, okay? Well, first off, any lithium that's in this compound is an ion. Basically all the lithium, 100%, is an ion, okay? None of it is not an ion. I guess that's a bit of important information because if I look at the formula, for every one formula unit of the compound, Li2SO4, okay, I put that in the denominator so the units cancel, but for every one formula unit of that stuff, how many lithium ions are present? Aren't there 2? Because of how the ions combine to balance the charges. I needed 2 of these for every one of these, so it's a 2-to-1 ratio in terms of its so-called stoichiometry, and the ratio of combination. All right? So as a result, I can take the number of formula units of the compound, just multiply it by 2. That means that I've got 6.8 times 10 to the 22nd lithium ions in this sample. Now, what about the sulfur? I think we're also, no, actually I asked about sulfate first. So let's talk about sulfate first, okay? So in the sample, we still have the same number of formula units of Li2SO4. So this first one again was for the Li. The second one now is going to be for the sulfate. How can we figure out how many copies of the sulfate ion we've got, okay? Well, as I look at this, I'm not too scared because I know I have that many formula units of this, and from the equation, it looks like I've got 1 sulfate ion for every 1 formula unit. Right? 1 copy of this polyatomic ion, remember it's a cluster, it comes together, right? 1 copy of that per 1 formula unit. So as a result, if I've got 3.40 times 10 to the 22nd formula units of lithium sulfate, I've also got that many sulfate ions. Same number, because it's a 1-to-1 ratio. All right? So that helps us with the lithium and the sulfate. Let's move on. We're also asked about sulfur atoms and oxygen atoms. considering the same sample, 3.40 times 10 to the 22nd, 4 million units of Li2SO4. Let's compute number of sulfur atoms, huh? How can we do that? Well, same way. All we need to know how many sulfur atoms per one formula unit of this compound. And as I look at this, I say, oh, it's just 1 to 1 again. I've got 1 formula unit of the compound. Within that 1 formula unit contains 1 sulfur atom. So it's 1 to 1. As a consequence, I've got the same number of sulfur atoms. But the story will be a little bit different, I think, for oxygen. I still have 3.40 times 10 to the 22nd formula units of the compound. That, of course, is the same. But the thing is now, for every 1 formula unit of this material, I've got 4 atoms of oxygen. Because you see this subscript 4 that comes with sulfate. So that tells us that the sulfate polyatomic ion is made up of 1 sulfur atom and 4 oxygens. It's a 1 to 4 ratio. So for every 1 of this compound, I've got 4 oxygens, 4 to 1 ratio. So what I need to do is I need to multiply that number times 4. Because if I've got 3.4 times 10 to the 22nd of those groupings, I've got 4 times as much oxygen. Right? Everybody see that? So I've got 1.36 times 10 to the 23rd oxygen atoms. Alright, so hopefully that makes sense. This problem is a really nice problem for a couple of reasons, okay? Again, when we started out, we had to write formulas for compounds from names. If I wanted to up the difficulty on one of these types of problems, I'd make you do that. You got to write the formula from the name. Another thing that's crucial for this problem is this idea of the types of things that we just did, where you had to take the element ratios, okay? Kind of like this 4 to 1 business for this compound. You have to have the ability to identify how many copies of a particular element is present in 1 formula unit or 1 molecule of a covalent compound. Okay, so really look at that and pay attention to it and practice it some, because those are really crucial skills for this chapter that have been demonstrated here by this problem 319. So I hope it was useful to you.